Unit 6, Section 1, Video 2. Let's do a couple examples here on this next page. So example number 2, Pete is building a new barn, and the table below represents his actual and his scale measurements. So this is to say that his actual length of the door opening, the wall, the water line are all in feet, but then he's doing a scale drawing, like on a piece of graph paper, and he wants everything to be to scale to see how much other room he has. So he does that in inches. So we're going to be using proportions to figure out how things need to be shrunk down and whatnot. So question A is, what's the length of the water line in his scale drawing? So here I'm going to once again set up my key to make sure I'm consistent. So I'm going to use the actual length, and I'm going to do that over the scale size. So I can use either 16/4, or I could use 25/6.25, because those should be equal. They should give me the same scale factor. And I'm going to use that to solve for our actual water line length, which is 10 feet, over our missing one. So I could do either of those. And then I'm going to solve for x. So if I was going to do this first one, I could say 16 times x is equal to 4 times 10. And 4 times 10 is 40. Divide that by 16, and I get that x equals 2.5. And so that was when we were solving for our scale length, and so that would be 2.5 inches. So that's how big he should draw it when he's drawing it to scale. If he recorded a scale length of 5 inches for a window, what is the actual length of his window? Alright, so that's kind of going the other way, but I'm still going to do actual over scale. So I'm going to use the same proportion of 16/4, and what I do know is that he drew for the scale 5 inches, so I'm going to put that on the bottom, and what I want to solve for is the actual. And once again, I could do either, so I could also do 25/6.25 equals x over 5, either one. And when I do cross multiplying, I get x equals 20. And because I'm doing the actual length, that would be in feet. And so I could do that either way. Once again, I could do 16 times 5 equals 4x and solve for x, or I could do 25 times 5 equals 6.25 times x. Either way works. And the last question is, if he measured his actual window to be 3.75 feet wide and recorded its scale measurement as 0.85 inches, is he correct? Well, I can figure that out by just setting up the equation and seeing if it works. So since our ratio that we've been using is 16/4, we can actually simplify that down just to 4/1. So that means our scale factor, and we'll get into a little more of what that is in the next section, is 4. Or we can think about it as 1/4. Once again, like I said earlier, it doesn't matter which one we put on top or bottom, as long as we're consistent. But since we've done actual over scale, we're going to use 4/1. And so if we think about 4/1, does that equal our actual, which is 3.75 feet, over 0.85? And we get that 3.75 divided by 0.85 is about 4.4. So those are not equal, therefore he was not correct. So it's all about just checking those fractions in the scale and seeing if he shrunk it correctly, and it looks that he did not. Example number 3 is applying a little more of what looks a little more like geometry to us, in that it requires figures and rectangles and knowing the properties of rectangles and squares. So, in simplest form, what is the ratio of lengths mn to mq? Okay, so if we're thinking about doing it as a fraction, we know the length of MN right up here is 16. And I'll just put that on top, and then MQ is right here, is 16. So that means the ratio is 1/1. You could say, you could also, sometimes it's just said as 1:1. And that's just to say that they are the same, they are congruent. So in simplest form, what is the ratio of the lengths NP and NP is this little piece right here, and that's 8 to MN, which we already looked at was 16. And we always simplify to say that that is 1/2. And now in simplest form, what is the ratio of the area of MNRQ to the area of NPSR? So we know area is length times width, and the area of MNRQ equals, so if we look at MNRQ, it's that square right there, so that's 16 times 16, which we get to be 256. And then the area of NPSR, so we think NPSR, it's kind of that rectangle there on the right, we get 8 times 16, because we do length times width, and our length up here is 8, and then our width is 16, and that gets to be 128. So our ratio would be 256/128, which we can actually simplify to be 2/1. And once again, we can also write it as 2:1 or write it in words of 2:1. So that means that the area for MNRQ is twice as big as the area of NPSR.